Hi, my name is Jason Woodworth from the CAX Virtual Reality Lab at the University of Louisiana at Lafayette, and I'll be presenting our work on the design and evaluation of visual cues for restoring and guiding attention in eye-tracked virtual reality. Okay, so first a quick summary of our work. Through it, our first main goal was to compare a large number of existing and novel visual cues that are meant to guide attention to specified targets within the world. Our second main goal was then to demonstrate a novel comparison task different from the standard guidance task seen in most works, and through this, show that different types of attention guidance tasks may necessitate different cues. To do this, we implemented 9 visual cues, both novel designs and ones picked and adapted from the literature, and compared them in a wide range of conditions, comparing cue performance in both attention guidance and restoration tasks. More on those definitions later. In our results, we give a prescription of which cues to use for different scenarios, and evidence that these different tasks create different patterns of cue effectiveness. For our motivation, we look to the importance of attention in the industrial workplace. In addition to attention's self-evident importance to productivity, a 2019 report by Screen Education found that about 1 in 4 accidents in industrial workplace settings were caused by a worker who was being distracted by something like a cell phone. Some of these distractions may even be necessary, such as a task assignment notification or workplace chats. We also look to the growing use of XR devices and mediums in the industry, as evidenced by our lovely workshop here today. These devices allow us to impose imagery in the world to guide and restore attention to necessary targets. As our example, we look to a VR industrial offshore oil rig training application, as are often developed here in the southeastern United States region. As you can imagine, in a training scenario, there are many moments where you may want to guide a user's attention to an unknown object or restore attention after the user suffers some distraction. So I've been talking a lot about these visual cues, but what are these exactly and what might they look like? Well, these visual cues might be anything visually rendered within the world that bring that user's gaze to a target within the scene. This has been the subject of research for a few decades now, and so there exist many examples of such cues. One of the most prominent types is the simple arrow, often rendered in the center of the screen or just in the user's periphery. These arrows tend to point to where the target is in either screen or world space and goad the user to look in that direction or towards that object. These are so common that they appeared in over 50% of the cue comparison literature that we surveyed for this work. Other cue types include highlights. These are typically rendered on or near the target itself. These include diegetic cues like a light bulb within the world, such as in this middle graphic, simple colored overlays, or even complex moving or flashing nearby indicators. Many other kinds of techniques have also been tried, such as drawing a path from the gaze to the object, creating a type of radar. For a fuller comparison, please see the related works comparison table in our full paper. So we selected 9 cues for our comparisons, picking some from the literature, modifying others from the literature, and contributing other novel designs. All of these utilize eye tracking from a Vive Pro Eye headset. These are as follows. First, the basic arrow. This is projected out onto the surface of a head-centered sphere with the sphere's radius being the distance from the head to the target. It simply points in the direction that the user is intended to look at. Next is an arrow trail. As the name suggests, it places an arrow along a trail from the gaze point towards the target, adding arrows to the path as becomes needed. This is the arrow field. This is a static cue placing multiple arrows in a fixed position all around the user, all of these point towards the target. Next is the dynamic S-wave. This is adapted from a work from Renner et al., and this places concentric rings on the head center sphere that are animated to move and close in on the target, with the movement speed, here, is being dependent on the eye gaze from the target. Then we have the border, analogous to the Halo VR technique from Grunfeld et al. Similar to the S-wave, this uses a ring closing in on the target, but the ring's size here is based on the gaze distance from the target. The vignette is a novel cue which creates a tunnel vision effect, effectively darkening parts of the world that lie away from the target when the user starts to look away from it. The line strip is a novel cue which renders a thick line along a cubic Hermite curve from a point 2 meters from the eye to the target. The attention funnel is adapted from Biaka et al. And renders a series of rings in a funnel shape along a similar cubic Hermite curve to the line strip. Finally, the highlight simply tints the target with a salient yellow color when the user is looking away from it. We also included a baseline no cue condition to compare all other conditions to. To compare these cues, we first present a standard guidance or search and selection type task. This type of task is what most authors typically use to compare visual cues in the existing literature. In this type of task, several potential targets are presented in the scene, and a visual cue is used to guide the user to the one that they are meant to look at or select. In our experiment, these targets are floating barrels from the oil rig environment arranged in two layouts, a wide and narrow target spacing. Each barrel is pseudo-randomly numbered 1 to 8, and subjects had to look at the barrels in ascending order. After they look at the barrel for a certain amount of time, it becomes activated, and the next barrel in order becomes the next active target. We also varied the amount of dwell time it took to activate the barrels between 1/8 of a second and 1 full second. From this, we extracted the total time it took a user to activate or select all 8 barrels, minus the required dwell time, and use this as our primary objective metric. Now, as I mentioned, this is the main task used to compare cues in the literature, but it does not necessarily reflect all scenarios one might face in the workplace. Important to this task is that the user has not previously seen the target, and they are being guided to a new one. But what if the user has seen the target, then was distracted from it, and now needs to return their gaze to the target? For example, someone may be working on a task, receive a notification on their phone, or see some unexpected movement in their periphery, and now need to return their gaze to the target. Would the same cues useful for attention guidance then be as useful in this attention restoration scenario? To answer this question, we designed a new type of attention restoration task. This task starts similarly, looking at barrels in a narrow or wide target spacing, narrow as shown here. But every 2 or 3 barrels, a distraction object pops up away from the target. The subject must then look to the distraction to clear it, and then they are led back to the target by a cue. In this, we also vary how many distraction objects spawn, 1, 3, or 5, and how far away they are placed, being near or far. From this, we compute the time taken to look back to the target after the distraction is complete as our primary objective metric. In our experiment, we first presented the restoration phase, which used a 2 by 10 by 3 by 2 study design, with the 4 independent variables being the target spacing, the cue, the number of distractions or distraction breadth, and how far away the distractions were from the target or distraction distance. This was followed by the guidance phase, which used a 2 by 2 by 10 study design, or the target spacing, the 2 target spacing conditions, then the 2 dwell time conditions, then the 10 cues. To be more specific, in the restoration phase, subjects were shown 1 target spacing condition, one of the 2, in which they used each of the 10 cue conditions to look at the 6 combinations of 1, 3, and 5 near or far targets. Then, in the guidance round phase, subjects completed 4 rounds with a combination of the 2 target spacing conditions and the 2 dwell time conditions, with each round using all of the 10 cues. We conducted this guidance phase with 98 subjects and got the following results for guidance time. This plot here shows the median guidance times per cue for each of the 4 conditions the cues were used in. Cues on the x-axis here are ordered by their overall median guidance time, that is, how well they performed across all scenarios. We then performed Friedman and pairwise Wilcoxon tests to detect statistically significant differences between the cues. In this matrix here, we show the number of significant differences found between pairs out of the 4 conditions they were compared with the sign here showing that the rose cue had a lower time and performed better than the column cue. So, for example, the highlight and arrow trail cell here shows a -2. This means that the highlight performed better than the arrow trail in 2 of 4 combinations of target spacing and dwell time conditions. Okay. From these results, we infer a general ranking where highlight, line strip, S-wave, and attention funnel generally performed better than all other cues. Then arrow trail, border, and arrow were somewhere in the middle, performing better than some and worse than others, and vignette, arrow field, and no cue performing worse than almost all other cues. Now, with the restoration phase, we conducted it with the same subjects, but due to recording errors, we're only able to use data from 67 of them. This plot here shows the median look-back times per cue for each of the 12 conditions the cues were used in. Cues on the x-axis here, again, are still ordered by their overall median guidance time, not restoration. This is done to emphasize the difference in the pattern of results. We can clearly see that these lines here do not follow the same general upward trend that we saw in the guidance plot. Now, once again, we performed Friedman and pairwise Wilcoxon tests to detect statistically significant differences between cues, showing a similar matrix here as we did before. Once again, we see a different pattern of differences than the one that we saw with guidance. Using these results, we then create a similar 3-group ranking. The top cues here are S-wave, highlight, and no cue. The middle cues being line strip, arrow trail, and border, and arrow. And then the worst cues being vignette, arrow field, and attention funnel. Of primary notice here is the way 3 of these cues shifted in their ranking. In guidance, the line strip and attention funnel cues were among the best performing, while for restoration, the line strip is only in the middle, and attention funnel actually has the highest median look-back time of all. To little surprise, the no cue condition was among the worst performing conditions in guidance, but to our surprise, it was actually among the best for restoration. We believe this points to a fundamental difference in task. When users do not know the location of targets, they clearly could benefit from some form of guidance. When they do know the location of the target, a subtle reminder to return to it, like the highlight, or even no cue at all if they know they need to return, might be enough. And attention-grabbing, in-your-face cues like the line strip and attention funnel might actually just further distract the users and make it take longer. So what can we take from all this? First, a list of recommendations. We suggest that the highlight cue is perhaps the quickest in all scenarios, possibly even being pre-attentive, but is only visible to targets within view. So if targets are to be spread all around the user, it may not be as appropriate. We then suggest the dynamic S-wave cue is quick and works with out-of-view targets, but the fact that the visuals take up much of the user's field of view makes it not as suitable for multiple potential targets. Finally, our novel line strip cue may be slower for restoration, but is still quick for guidance and can work for multiple out-of-view targets. Next, we consider the clear differences in performance order found between the guidance and restoration tasks. Given this, we ask if there are other common attention-related tasks that may show different patterns of effectiveness that could be tested as well to ensure that those tasks are being met with the appropriate cues. Finally, we consider a limitation of our work to be that we used controlled distractions that we forced the user to look at, used a single shape as the target, the barrel, and only tested single target scenarios. We are currently addressing some of these limitations in an upcoming educational project that we're deploying for real testing in high schools. For further discussion on the cues and other independent variables tested in our study, please refer to our paper, and we thank you for your time and hope you enjoy the rest of the conference.